For this unit, we will be covering the topic of recursion. Recursion is a way of thinking and a way of programming that is a little bit different from what we've covered so far this year, but is equally useful to understand and to get to know. So far this year, we've covered how to loop through arrays, different sets of data, and that looping is known as an iterative solution. Iterative just means that I go through every element within the array or every element within a loop. A recursive method or a recursive style of programming is one where the function will call itself. That function calling itself is really just breaking down a task into smaller chunks that can be done again and again and again. Kind of like the cat in the hat picture on the side where each call is just a different cat inside of the hat. Recursion is useful when we can break down a task into many repetitive steps. We've seen recursive functions throughout math with geometric series and sequences with the Fibonacci sequence. But within computer programming, recursion is particularly useful when there are many decisions that need to be made throughout your method's execution. So, for example, on the side here, we have a binary tree, many different outcomes dependent upon the decision that you make. Recursion is particularly useful in finding certain outcomes quickly, where an iterative solution would have to take into account all the different logic that would be needed to find that end node with the decision that we'd like. Those nodes can kind of be thought of in terms of pathfinding or maze solving, and that's useful for robotics, video game design, whatever you need to find the shortest distance for a path. And they're also useful in certain art pieces. We can see an artist going down the rabbit hole, if you will, of the piece of art that he's drawing. There's also other geometric art such as fractals and others that you can search on the internet to find that are recursive in nature. So when would we use a recursive solution against an iterative solution? And the good thing to know is you can use either. There will always be a solution using both types. So if a solution makes more sense to you using a loop, then you can always use a loop. Recursion is just sometimes a little bit more elegant and easier to read and understand because sometimes it will be shorter in terms of the amount of code that you actually have to write, but the hurdle is understanding exactly how it works first. So there is that initial leap you have to make in order to kind of think more recursively. And that is a struggle that most students have with recursion. Recursion is sometimes a lot less efficient just because there are many tasks that a recursive function calls, where an iterative solution just uses the loop and completes the task from there. A recursive algorithm always has to be made up of certain parts. The first piece that we need to know is the base case. A base case lets the recursive function know when it needs to end. Just like a loop, we could loop infinitely. A recursive function can also call itself infinitely. So every recursive algorithm needs a base case, which is just when it stops. As we are calling each new function, there has to be a process where we're working towards our goal. So each new function call needs to get closer to the end, closer to that base case. So let's say we were counting down from 10. The next movement towards that base case needs to just be one less than the previous call. And then finally, it needs to call itself in order to be recursive. So for example, if I'm walking home, then I need to take one step closer to finding my way home and then call that recursive function again. Take one step closer, recall the recursive function, take one more step, call the recursive function, take one more step until I've reached whatever the home destination is. Then I can stop moving. That would be my base case. So I keep moving and checking, moving and checking, moving and checking until I've hit the destination. So here's a look at that maze algorithm that I alluded to before. There's actually really not a whole lot going on in terms of the tasks that are needed to solve the maze. So here's your base case. Did you hit the end of the maze? Once you've hit the end of the maze, that's when you stop. The other commands are look to the left if you can go to left, look to the right if you can go right, up and down. If you can go to the left, then you're going to call on your next recursive function. You're going to say, okay, if you can move to the left, now we're going to look left, right, up, or down. If you can move to the left, then great, we're going to look left, right, up, or down. If you can't go to the left, then you're going to go to the right. So, as you can see with this animation, the search for the end, as it goes, it does reach some dead ends and says, oh, I guess I can't go that way. I'll need to choose another option. When all of the options are exhausted, then it will go back and retreat to a previous node that was useful. If we look specifically at this spot where it needs to make a decision, there is a visual I like to use for recursive functions that I think will make a little bit more sense. So here I am standing at a node within my maze. And here's how a recursive function would work. I want to explore this section of the maze to my right. Instead of myself going down that corridor to see what's at the end of that maze, I'm going to call another me. I'm going to say, you go down that corridor and see what's there. Now they are going to follow the same rules that I did. They're going to say, oh, I've reached this node in the corridor and I have to say, can I go up, down, left, or right? It's going to say, hey, you go down that corridor and you see if you can find an end to the maze. They are going to say to themselves, oh, look, I'm going to go up, down, left, or right. Let's find out whether there's the destination. They're going to call another one of themselves and go up, down, left, or right. They go to the left and they say, hey, this is a dead end. We can't go here. And he'll report to the last person to call him. The last person says, okay, fine. I guess I can't go to the left. I will go in one of the other directions that I can choose and then go to the right. They're going to call someone else who will then say, I can probably go down. And then they're going to call someone else and they're going to say, hey, I've reached a dead end. I can't go that way. So this, Galisi says, I don't have any other directions I can go. We must not be able to go down this way. All the people I sent out, they say we can't go this way. All the people we sent out, they say we can't go this way. All the people we sent out, they say we can't go this way. So that original Galisi knows that to the right is not a good destination. So he just came from the left. So now they're going to do the whole process over and say, okay, great, I'm going to go this way. And that is basically how recursion works. You delegate the work to other recursive function calls. They do their own work and delegate it to other functions until eventually they all notice that they don't hit any more dead ends and they run all the way to the end of that maze. A terrifying example, but hopefully something that makes a little bit of sense. Now we're going to compare two pieces of code that do the exact same thing. They're going to print from 10 down to 1. The first is a looping solution, with just starting at x, whatever x we say, let's say it's 10, and printing each value. And then the exact same result, but recursively written. So the first thing we always need to take into account is when are we going to stop? That stopping point is our base case. We're going to stop at 1. And when we do hit 1, we're going to print 1. The other portion of that recursive method is going to be a move towards the goal, which is x minus 1, and a recursive function call. That would be the recursive printing, which is its own method. So if we had 10, 10 would not hit the if statement and would go to my else. It would print 10 and then run 9 on the original function. So we go back here to the function that we were running. X would be 9, would skip the if statement, and then print 9, call 8, the function call of 8. It would call 8, 7, 6, 5, 4, 3, 2, 1 until eventually 1 would be enabled, print 1, and then the entire function would complete. Now, what you're probably saying is, that's really stupid. Why would I ever print like this recursively? And the answer really is you'll never will. The for loop is a lot more efficient, a lot easier to understand for this type of action. But we look at this recursive function just for the sake of learning how recursive methods are made. And you could probably see the complexity that recursion would be used for in terms of maze solving or other more difficult to write methods. So let's look at something that is a little more efficient when it's written recursively. Here's the Fibonacci sequence. The Fibonacci sequence relies on the previous two terms to get the next term. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, so on and so forth. If I were to write that iteratively, then that takes a lot more work than if I were to write it recursively. And the thought process is, if I know that the Fibonacci sequence is just the two previous terms added together, that's exactly what you're going to write for the recursive function. I just look at the nth number, and I've just noticed that I wrote nth number instead of n, so we're going to pretend that says n. We're going to look at the previous term and add it to the previous term to that. We're going to keep doing that until we reach a 1 or a 0. So you can kind of think of it working backwards. If I want to get the 7th term, I'm going to start at the 7th term and work my way backwards until I hit a 0 or a 1, and it will add them all together. Our last example looks at factorials. Factorials, if we remember from our math courses, is just the multiplication of all of the values that follow the nth number. So if we have 4 factorial, it would just be 4 times 3 times 2 times 1. Okay, so if we were to try to write this recursively, there's a few rules that we have to remember first. When we do 0 factorial, that factorial value should produce 1. Any other value above that should call the previous multiples behind it, the previous values that we're going to multiply behind that value. So that base case, when n is equal to 0, will tell us where to stop. It's just going to return 1 when n is equal to 0. So if I were to call anything above that, I know to multiply up until I reach that value of 1 or the value of 0. Notice I said 1 or 0. If I give 0 as the value for n, there is no multiplying being done. The same thing with 1. So my base case is when n equals 1, I'm going to return, or sorry, when n equals 0, I'm going to return 1. When n equals 1, I'm also going to return 1 because there's nothing to multiply. Otherwise, I'm going to work towards my goal being 0 or 1, and then multiply the current term times the previous term. So we're going to walk this through and show you exactly what will happen with a recursive function when we are calling the previous method. So given the recursive function for factorials, let's say I know that the value for n is 4. So I know that should be 4 times 3 times 2 times 1. Yeah? So as n is going through the if-else statement, 4 is not equal to 0 or 1, so it's not going to return 1, but it will call 4 times the function of 3, because n minus 1 would be 4 minus 1, which is 3. That function call immediately goes to a brand new factorial method. That factorial method plugs in the value of 3. So 3 doesn't trigger the if statement. It will go to the else, which would say n, which is 3 times the function of 2. The function of 2 immediately calls the next method, which would be 2 times the function of 1, until eventually the function of 1, when n is equal to 1, will hit this base case. That base case no longer calls any more functions, but will say I'm going to return a solid value of 1. Now here's where it gets interesting. At this point, just like the maze, where I sent people down the path to see if the work, or to see if the path led anywhere, this is the first time, once I've hit the base case, where I have a solid value. All of these other lines were in process, unresolved function calls. These are all still open, still waiting for the person down the corridor to come back and tell them whether they found the end or not. This is the end. We found it, the base case. So once this returns 1, that function value is worth 1. 2 times 1 is 2. So this function is worth 2. 3 times 2 is 6. This function is worth 6. 4 times 6 finally gives me an ending result of 24, which was the 4 times 3 times 2 times 1, which was also 24 that I was looking for. That is how that recursive function works. The call to the method n minus 1 keeps going until it reaches that base case, until a result is found. Here's a brand new example that you should try. It uses recursion, and n is equal to 4. So what value, once it reaches its base case, will be the thing that it returns after all is said and done? Give it a try. Use the example that was just given to you a moment ago to see if you can diagram your own recursive result. All right, let's talk about the solution real fast, and then we will be done. So when n is equal to 4, it does not reach my base case. So it will say 3 plus the function of n minus 1, which is 3. Then it will say 3 plus the function of 2, 3 plus the function of 1, where 1 will finally return a value of 2. We've hit our bottom, we've hit our base. So this whole function is worth 2. So the entirety of it together makes 5. This whole thing would be worth 8, and then the entire thing altogether would return a value of 11 once it's reached the end. And that's it. So the Beginning of learning recursion is a tough mental shift. Please leave any questions or comments. We'll be happy to address any and all questions that you have. And to make you feel just a little bit better, here's the creepiest photo of recursion that I could find on the internet of Hulk Hogan. I hope you enjoy, and we will see you soon.